Hey everyone, welcome back to another podcast. I hope you are enjoying your Saturday and are getting ready for the holiday season. Today I want to talk about an article I was reading, and basically it addresses the question of, are we living in a simulation? Yes or no? Now, at the end of the article they say that it's about 50-50. So it's about a 50% chance we are living in a simulation, and there's a 50% chance we're not living in a simulation. Now, they kind of talk about the original, kind of where this originally came from, which was in a 2003 paper by an Oxford University professor. And other famous people, such as Elon Musk, have, thrown their hat into the ring, and so to speak, and have said that we are living in a simulation. According to Elon Musk, there's a 1 in a billion chance that we're living in a simulation. Now, my own point of view on this is that we are definitely not living in a simulation. And even if we were, there's no way to tell. It's what I like to call one of these unanswerable questions. And what I mean by this is that forever, until the end of time, whatever that means, we will forever remain ignorant of such a question. It's not a actual answerable question. So people have kind of put forward reasons why they believe that we do live in a simulation. So I'll give Elon Musk as an example. So Elon Musk has said that because of the rapid rate of technological advance that we've seen, it's reasonable to assume that if in the future, every year we increase the complexity of that technology by a factor that's non-zero, it doesn't have to be a huge factor, but even if it's non-zero, that essentially means that at some point, in some limit, we're going to reach a state by which we can simulate the human experience, let's say in a video game. We could create a human being that we can completely simulate their world, and they would not know if they were or were not in this, simulated environment. So you could think about how you would logistically do that. Maybe in The Simpsons, there's an episode where they have a big glass dome over the city. And maybe you could do something like that, where you would program basically weather, and you would always ensure that the humans inside never try to go past a certain point. So they would never be interested in leaving some area. Maybe you could do this somewhere on the earth, like a whole continent. You have the whole continent as that. Maybe you project a huge ocean or something, so they would never think to go out there. So there's many different kinds of ideas you could come up with as to how this would actually work. But basically, if you can do this in a computerized way, sorry, I should mention it's computers, then it's a proof that we could be living in a simulation. Now, I don't really think that simulating something in a video game per se would be equivalent to being able to simulate biological systems, for the main reason that biological systems will forever be more complicated than any computers we come up with. To be quite honest, the computers we have are very wonderful. They do a lot of cool things, but at the end of the day, it's literally zeros and ones. There's a lot of magic that appears to you because you don't understand, and because actually the processors are so quick that you don't even notice that a lot of the things that you see on your computer are just really fast execution of code that is literally just getting transcribed into zeros and ones. So I think the most point, the technology we have right now, although it's very nice and it's very wonderful, we are so far away from doing any kind of biologically relevant simulation of anything. For example, people who work in jet propulsion laboratories at NASA. So right now they're trying to use machine learning techniques, because if you want to simulate what it's like to fire a rocket and look at all the jet fuel coming off the jet stream, the data required to compute the vector field, which is basically at every single point in your simulation, which would be a grid, you want to be able to compute using the laws of fluid motion. You want to be able to compute how those values in all these grid positions, how those values change over time. And what you do actually when you simulate things in time, which they never tell you, is that you have to basically sample at every point in time. So you take a grid of points. So you'll take like 0 to 1,000,000. So the more points, the more time stamps you take, the more data you have. This is just the way it works. And then what you'll do is you'll plug in values at each of these time intervals, and you'll see how the values change over time. And we have some really good numerical algorithms for doing this. But basically, the problem is that these algorithms take, to compute like 1 second, I think this is what they said, 1 second of a jet stream. So basically a very small rectangle that just shows how the rocket is coming, all the stream from the rocket, what it looks like. To compute a 1 second video of this takes like 2 or 3 days of computing time with a very sophisticated supercomputer right now. And these are using, the best kind of hardware techniques and that kind of thing. Now, basically what they do now is you can take these, use the physics-based simulation, which is what they're called. You're actually using equations from physics to simulate things. What you'll do is you'll transcribe this into a machine learning problem. And the way you do this is that when you do simulations, it's basically producing one image. You're just producing tons of images. And then when you play a video, it's just showing you those images, 60 frames per second, which is why it's called frames per second, because it's image, and you're seeing 60 images every second, which is a lot of images, but that's basically how it works, right? So what they do now is you feed image data to basically like what's it called, a convolutional neural network, and the convolutional neural network can be trained to understand implicitly what the laws of physics are from the simulations. So it's kind of like just learning how to do something from watching someone else do it. Basically, the machine learning algorithm doesn't need to know the physics, because the model that you trained using the physics, so the physics simulation has all of the information that you need encoded in it already. So that's already done the heavy lifting. Now you can use machine learning techniques to basically extract the most important information. And what they're doing now is sorry, I've really gone on a tangent here, but you can pretty much get rid of a lot of the data. Like we're talking like gigabytes and gigabytes of data here. You can get rid of a lot of it just using these machine learning models. So, I mean, within like a second, it's pretty accurate. When you go past a second of clip, it's pretty inaccurate because it doesn't have any of the physics in it, right? But anyway, one of the other arguments Elon had was kind of talking about Moore's law. And a lot of computing has to do with transistors. So transistors are one of the most important parts of the computer, and they actually gave rise to computing, because the transistor is what tells the machine if it's a 0 or 1. So we have billions of transistors on our computer, which means we can store billions of bits of information, because one bit is a 0 or 1. So it's one position and it's a 0 or 1. A byte is 8 of these, and you can keep going on. 8 bits, and you can keep going on and on and on and on. The bits, go up in factors of 10. So a byte, I believe, should be 10 zeros and ones. But anyway, not important. And the transistors are the most important thing. So we've been able to pack more and more transistors into computers, which means we can store more and more information. We can compute more and more information. And that's been going up at we've been able to fit 2 times as many transistors into the computers every 2 years. So the doubling time is about every 2 years. Now, this is called Moore's law, and I'm very suspicious that it's ever going to keep continuing, because they call it a law, but it's not actually a law. It's just an engineering fact. So there's nothing that's a law about it. It's basically just a fact. And this fact is going to stop, in my opinion. At some point, there's not going to be a doubling. Maybe there will be a non-zero, greater than 1 factor of improvement every year. But I highly doubt that this doubling of transistors every year is going to continue for much longer. So basically what I'm trying to say is, Elon seems to think that if we just keep going on and on and on forever, we are eventually going to hit this kind of ability to have computers that are just so advanced and so complicated that they're going to be able to simulate the world. And if we can prove that we can simulate the world, then we can prove that we can simulate ourselves, like we will live in a simulation. I really don't believe this because basically the only way to get around the classical world of computing of zeros and ones is that you need to invoke quantum computers. And it's not very clear that quantum computers can actually do everything that a classical computer can do. So, for example, could a quantum computer find a way to simulate all of the rules of general relativity? Because that's a very important physical theory. I don't know. Maybe it can, maybe it can't. But quantum computers inherently rely on the fact that you can reformulate classical problems as questions of probability. So if you cannot do that, then you cannot use exclusively a quantum computer to do a problem. So what I want to say about this is that quantum computers, what they do very well is they perform, they can search through a sample space, meaning they can search through all the probabilities in a much shorter amount of time than a normal computer can. So most famously, there's an algorithm for computing the prime factors of numbers. It's called Shor's algorithm. So Shor's algorithm was discovered in 1995 by Peter Shor. He was a mathematician. And basically what he showed is that, let's say you give me a really, really big number. I'm talking about like 100, 200 digits long. And we know that this is a prime, it's not a prime number. It's a composite number. Actually, this would be longer. RSA 245. Sorry, a 2000 digit long number. To be more specific, 2048 digits long. And this number is a composite number, which means that it's the product of two prime numbers. So you have to multiply two numbers to get that number. Now the special thing about this composite number, this 2048 digit number, is that this number uniquely factorizes into these two really big prime numbers. That's the most important thing about that. Because, for example, you could just give me like a really big number that's like an even number, huge number, like some factor of 10, like 10, 10 to the 2048. Okay, huge number. But if you want to factor that number, it's going to have tons of multiples of 2. It's going to be like 2 to the something, like 2 to the 100 something maybe. So like the number of prime factors is going to be massive. It's going to be there's going to be a lot of prime numbers that you can keep breaking it up into. When you were younger, you drew those trees, if you take the number 25, okay, what are the next factors of 25? Okay, 5 times 5. Okay, that's about it. 10 is 5 times 2, and then you can't go any further there. 30 is 3 times 10, but 10 can be broken down into 5 times 2. Okay, I'm done. So you would do that with this really big composite number, and basically you can get these two really big prime numbers. So anyway, Peter Shor showed that you can reformulate finding these two prime numbers of this composite number that's really big. You can reformulate this as a probability question, because you're basically asking what is the probability that you're close to the prime numbers that you're interested in. So, and the way that this works is you want to find, actually I won't go into it, it's very complicated. But basically you can reformulate this as a probability question. And then what you can do is you can ask, using this algorithm, using quantum computers, you can ask, where is the most likely position for the prime factors of this particularly long number? And it will tell you, 97% certain that it's in this interval, 1 billion to 1.5 billion. There's a 95% chance. And then basically what you would do is you actually do need to use classical computers, because at that point, once the quantum algorithm tells you the interval, then the classical computer can solve the problem efficiently, because the classical computer generally does a brute force. It literally looks at every single number, and it has to do, if you have a 2048 digit number, it has to do all of the numbers up until then, which is ginormous. It's a huge number. It's a huge possible number. So it's not that a classical computer couldn't find the prime factors. It just can't do it at all efficiently. So basically, when we talk about the simulation hypothesis, we have to make this assumption that our computers are actually going to be able to, for example, handle the kind of data, the kind of graphics, the kind of experience that we have as human beings, which I actually don't see how that's possible. Classical computers are very wonderful. They're very nice machines, but they really can't do, at this point, there's not really an ability to generate such a reality. So I feel very skeptical of that. Another thing is that I make a very big distinction between us and machines. So one of the simplest ways that I see this is that machines are amazing at doing things such as math. Human beings suck at math. We're terrible at math. We have absolutely no idea how to get accurate answers for, doing things like multiplying numbers that are bigger than 3 digits. It would take you a very long time. Division takes a very long time. Adding numbers also takes a long time. And it's not that you can't work it out, but a computer can do the same kind of computation in a ridiculously smaller amount of time. A factor of billions, millions, I don't know. But it takes a lot less time for an algorithm to do that. So I think that in that sense as well, the simulation cannot rely upon numbers. It cannot rely upon just using simple numbers to represent everything about reality. Numbers are not going to be what the reality that we live in is made of. So numbers are great for pattern finding, because in reality, numbers are not these kinds of entities, because I could have $5. I could also have 5 atoms. So clearly numbers do not belong to any particular class of objects that we see. For example, I could have 5 iPads, I could have 5 crayons, but these things are not all the same. And yet I can use numbers to describe them. So it's very clear to me that, numbers are not unique entities in this world. And so therefore, if you want to build a simulation, numbers would be the incorrect way to build such a civilization, or to build such a simulation, because it just does not work like that. It just does not work like that. And also we have good arguments from numerical simulations, such as, the errors. Because if you're in a simulation, the idea is that you'll have access to all of these physical laws. And then basically, how video game creators make physics engines. So for example, if you're playing games like, like Far Cry or something, they might have like a physics engine, or FIFA is a really good example. FIFA will have a physics engine where the balls that come in, it will track like the velocity, it will track all these things, and it will determine when you make a header where that ball's supposed to go. And it will actually program in F equals MA. But as you can see, FIFA's terrible. It's really not good. And it's not really clear that, even in modern computing terms, that those programs are getting any better, because they always have glitches. There's never been a time I've never seen that, So our reality, our physical reality, seems to work pretty much all the time. There's never a time that gravity hasn't stopped working. You've levitated for a minute, right? That's never happened. Whereas video games, for example, these things are full of bugs. They're wonderful, they're great, but they're not, in my opinion, at all like the real world. They're not at all like our physical universe. So I'm very unconvinced about this simulation hypothesis. I think it's a very interesting idea, but ultimately an untestable one. And pretty much it has no real basis for interpretation, because what does it even mean to be a simulation? What does that even mean? I don't think it's possible. I don't think it's possible. And I think, basically, someone would have to actually explicitly define what it means to be a simulation, because simulations always mean numbers. They always mean numbers. There's never a situation that they're not numbers. So I would have a hard time believing that just numbers would ever be enough, or just physics or just math would be enough. I don't think it's possible that that's possible. Not to say that maybe we aren't living in some kind of simulation, but I don't believe that we're living in the kind of simulation that people often talk about. I don't think that's true. So, and I also would not recommend you to live your life as if you were living in a simulation and that you thought you were. So anyway, I'm going to continue talking about this later on, but for now, I'm just going to upload this. Thank you very much for listening. And if you've gotten to this point, hopefully you tune in for the next episode. Thank you very much.